Right, this is chapter 2, accelerated motion, so you should join me on page 11 with some paper and press pause when I say, you get me? Word up. Right, defining acceleration on page 11. Acceleration is the rate of change in velocity. So if your velocity changes, that's an acceleration. How quickly it does it is called the acceleration. Okay, so there's some information talking about that. There's loads of situations where the velocity changes, and a velocity change can involve a speed change or a direction change, because you know very well that velocity is a, yes, it's a vector. You got that, didn't you? Did you got that, didn't you? Okay, so that's page 11, showing you some examples of accelerating objects. If at any point you want to read the book, press pause. Okay, I'll tell you to press pause for questions, but you can press pause yourself. It's there for you. You can shut me up. Okay, so turning on to question 12, finding acceleration. Okay, it's the rate of change in velocity. So acceleration is change in velocity divided by time, and that equation is given to you in your data sheet. So do please read that. Okay, you can see what it's looked like in the book. Okay, so there you go. There's the book. It looks like that. That's with symbols, change in velocity, v minus u. V represents the final velocity and u is the initial velocity. U comes before v. Okay, everyone gets this wrong if they're going to get something wrong, but the units of acceleration, because it's change in velocity divided by time. So it's meters per second divided by seconds as far as the units go, which end up with meters per second squared. Okay, there's 2 seconds on the denominator. So just get that right, meters per second squared. There's 3 worked examples if you want to look at those on page 12. Okay, if you want to have a go at some questions yourself, then they are on page 13. Just remember the minus sign in front of acceleration implies it's a deceleration because it's in the opposite direction to the velocity. So if that's positive as a vector, and the negative vector of acceleration would slow it down. Okay, if you want to have a go at the questions on page 13, have a go now. Press pause. Okay, you're back. So you can look at, again, motion graphs, looking at acceleration. They look identical to the graphs you looked at in the last chapter, displacement time graphs, but these ones are a bit tricky. Just think again what the numbers mean. Okay, so if you're having a little look at these graphs this time, on this graph, this is velocity. Okay, so as the velocity that way, if it is going up, then it's increasing velocity. So this line shows you the velocity is increasing. And because it's flat, it says it's a constant acceleration. So this is a constant acceleration, that's a constant acceleration, but it's higher. This one is flat. Now on the other graphs that means it's not moving, but on this graph, just be careful. Check what that says. It says velocity. So on this graph, the velocity, whatever value that is, stays constant. So it's a constant velocity. Okay, it's moving at a constant speed in a certain direction. Okay, negative means that it's going and decelerating. Okay, it's a negative gradient, it's a negative velocity. No, sorry, it's a negative acceleration. So on this graph, gradient is acceleration. That's a negative acceleration. You're slowing down. On this graph, it does curve and gets flatter. If the gradient gets flatter, the acceleration gets less. So this is something that's basically it is increasing in speed, but the rate of acceleration is getting smaller and smaller and smaller. If that flattened out, which it would do in something like terminal velocity, then there's no more acceleration and it stays at a constant speed. And you can read off the numbers off the graph. So that is quite simply what velocity time graphs show. They're totally different to displacement time graphs, but don't get confused. Okay, if you turn to page 14, it shows you can work out the gradient using the numbers again, because the gradient is quite simply a change in velocity on the y-axis divided by what's on the x-axis, which is just the time. Okay, and that will give you the gradient, and again that's the acceleration straight away. Okay, so you can have a look at that if you want. But on page 14 it then talks about displacement, and displacement on these graphs means something too. So on this little picture here, you've got, quite simply, the gradient of the line is change in speed over time. That's acceleration. On this graph, now it's hard to see the actual lines here, but if you've got a flat line there, okay, then you're going at 20 meters per second for 15 seconds. Okay, the area under the graph is this times this from your maths. Okay, but it's basically a velocity times time. Velocity times time is displacement. So the area under the graph is displacement. If it happens to be a triangle, it's just the area under the graph, which is a triangle. Half base times height, using the numbers. Okay, if ever you get a curve, all you have to do is draw a tangent to the curve, and measure the velocity of that. It might say that later on in the page. But if you have a go at the question, page 14, question 4, press pause. Okay, moving on, there's actually another 2 questions after that, page 5. I'm tired. Question 5 and question 6 on page 15, so you can have a go at those 2 as well.
Yeah.
Press pause. Okay, right, going on from that, you can find velocity and acceleration again in the lab, perhaps using a light gate. Now a light gate would notice if it had a card, which it says here, yeah, if you've got 2 bits of card sticking up, then one time it interrupts the light beam and then the second one does, and there's a change in speed. So there might be one goes through faster, quicker time, and as a result you can find a velocity for both, change in velocity divided by the time, and you can do it like that. So there's some little information about that, and then there's a bit more information about, in a car crash, rapid deceleration on page 15. That comes in car safety later, but there's a little device there that measures sudden accelerations by the actual piece of equipment doing something. But basically, read that. It's a very quick acceleration or deceleration, an airbag will open, because they know that something unnatural has happened to your car. Okay, moving on, question 16. Again, talking about ticker tape. You don't probably need to know this, they just like talking about ticker tape, because it sounds like a ABBA song. Ticker tape, ticker tape, ticker, ticker, ticker tape. If you change your... No. Okay, right, but anyway, if you've got ticker tape, again, you can just look at it by looking at how the dots, the acceleration is cleared, the increase, you can work out velocity from 2 dots far away, and then that velocity and the time difference between that and the previous velocity, you can work out acceleration. Okay, just read that page if you want to know, but it's unlikely they'll ask you that. Okay, but page 16 again talks about looking at motion sensors and accelerometers. Have a little read, just some information if you're interested, and then there's some questions on question 7 on page 17 you could probably have a go at. Press pause. Hello. Right. Equations of motion is next on page 17. Now these are the big boys, okay? Basically, if you have got a uniform or constant acceleration, then you can use the equations of motion. And the equations of motion, sometimes people call them SUVAT equations because of the letters we use to represent the quantities in the equations. Okay, so if you have a little look on page 18, you should know these. You should never look at the letter S and think that is anything other than displacement. Page 18 this. Okay, U, V, A and T. See what they are. You should know what they are. And then it tells you what the equations actually are. So you go through the 4 SUVAT equations which will be given to you. So basically, quite simply, what you need to do is whenever you do a question like this, you write down what you know, and you can see what equation to use, and then you can put in the right values, being careful of vectors and direction. If one thing is in the opposite direction to the other, it's going to find you, it's going to get you unless you deal with the minuses properly. So make sure you put in the minus values where you need to, or else you'll get the wrong numerical answer. Okay, so that's on page 18 there are worked examples 4 and 5, but hopefully you've done so many of these they will be straightforward and you know how to start. Okay, they are so important. On page 19 there are other worked examples, so why don't you have a look at those and press pause to have to see if you can do those. Okay, press pause. Good. Right, page 20. It's just all about practice with these. Okay, so can you just make sure you're being consistent with units, make sure you rearrange the equations properly, and make sure that you do the other thing that I've forgotten what I was going to say. Make sure you whatever, get them right. But all the answers are there obviously, but have a go at question 10 to 12 on page 20. If there's something you don't understand, bring it with you to the lesson and I will help you. Okay, so press pause, do those. Right, it does say in the specification you should be able to derive the equations of motion from graphs. Okay, so you're just going to have to learn this. Okay, hopefully it won't ask you, but it might. Okay, and if it does, you need to be able to do it. So if you have a look at this, it describes it all dead clearly how to do it. Okay, so they draw a little graph like this. It's a velocity time graph. So quite simply, if you do a velocity time graph, initial velocity u, final velocity v. Okay, change in velocity there is v minus u, it says. Okay, so that means that this little rectangle here, this area underneath this rectangle is the displacement. Okay, so it's just u, that value, times t, ut, which is what's in the green box. This one is half base. Okay, half base times height. Okay, and it says here the height is v minus u. Okay, which you can. Actually, does it say that yet? Yeah. Okay, so v minus u there, and the time is t. So it's basically v minus u times t. But they're saying here v minus u is equal to what's that symbol? I can't even see it. I'm enlarging. There you go. Yeah. Okay. So they've got it written in the textbook, v minus u equals at, and you know that because acceleration is change in velocity divided by time. Okay, so that is basically change in velocity, which is essentially at times t, times a half at squared. So that's 1. Displacement is the area under the graph, so it's ut plus half at squared. That's one SUVAT equation. Okay, so that is one of those that can be derived from that. Okay, the simplest thing saying to you is the gradient of the line is acceleration, and the gradient of the line is v minus u over t. Okay, the y-axis divided by the x-axis. Change of velocity divided by time. That's the first one. Rearrange that and you get it. Okay, the second one is saying displacement is area underneath the graph. Okay, so if you look at this, the average velocity, okay, is halfway between the two. So that plus that divided by 2, which is there, and now the area of that graph. So it's v plus u divided by 2. So that's the area. That's where you are, the height now. Okay, so it's u plus v over 2. That's the height times the distance, which is time. So it's v plus u over 2 times t. That's displacement. Equation 2. Thank you, graph. Okay, the next one, basically the next few just go into substitution, okay, and it's basically from equations 1 and 2 you get equation 3, which it says at the top. But to be honest, you just need to look at those and just learn them, and hope they don't come up because they haven't in 9 years, but you never know. Okay, so the next two just come from there, so have a little read of that now. Press pause. Good. Right, there's loads of context they can put SUVAT equations into. Okay, whatever it is, if it's got uniform acceleration, then use it. So on page on page 21, chilly. On page 21, you've got some questions 13, 14. Have a go at those. Press pause. Watch the vector. Okay, uniform and non-uniform acceleration. Now this is the difference. Okay, if you've got a curved line, the acceleration, like we said before, on the 21, bottom of page 21, you've got velocity that is decreasing in its rate of change, so it's getting flatter. That means the gradient gets less, that means the acceleration gets less. So you can see a tangent that's been drawn. Okay, higher up, quite simply, that is much less gradient, so it's got smaller acceleration. The velocity changes less in a certain time. The rate of change is less. So that is showing you acceleration, where the rate of acceleration is getting less and less. That's non-uniform acceleration. Okay, so it goes through on page 22 how to draw tangents and how to get gradients from that. So if you have a look at page 22, there's a question as well you can have a go at yourself on question 15 on page 22 and question 16. In fact, just do them both. Why not? Press pause. Did you do 17 as well? Why not? Do it. Press pause. And question 18 and 19. Did you do those? Oh, and 20. I'll keep going to the end, shall I? In fact, you know what? That's the end of the chapter. Have a go at the questions. Okay, and if you can do those, brilliant. Again, they are getting towards what sort of things they might ask you in an exam. Okay, there is a summary again at the end of that section. So if you have a look at that on page 24, and then there is actual exam questions, proper exam questions, right at the back on page 25 to 26. So have a go at those and see how you do, exam style. Okay, good luck, and anything you don't get, come to the lesson and ask. Okay, toodaloo.